Hi everyone, my name is Dipanshu and today I'm going to talk about sequential decomposition of stochastic Stackelberg games. So Bayesian Stackelberg game is placed between two players, a leader and a follower. A follower has a private state that only she observes. However, the leader knows the prior on that state. The leader commits to a strategy that is observable to the follower. The follower then plays a best response to the leader's strategy to maximize her utility. Knowing that the follower will play a best response, the leader commits to and plays a strategy that maximizes her utility. Such pair of strategies is called a Stackelberg equilibrium. It is known that such strategies can provide higher utility to the leader than obtained in a Nash equilibrium of the game. In the past decade, Stackelberg games have been used extensively in many real-world security problems, such as to protect ports, airports, wildlife. Such games are also currently being used by the security agencies, such as the US Coast Guard for the Staten Island Ferry, and Federal Air Marshal Service and Los Angeles Airport Police. And similar algorithms based on Stackelberg games are being used in wildlife protection in Uganda and Malaysia. So in this talk, I'm going to talk about sequential decomposition of such dynamic games. And one question I want to get to before is what does sequential decomposition mean and why is it so important? So in dynamical decision process, the space of the information increases exponentially with time. So if I take any action AT, it is a sum function GT of x1 to xt. So x1 to t basically lives in a space that increases exponentially. And thus the possible number of strategies increases double exponentially with time. So GT belongs to a space that is in the cardinality of A to the power cardinality of X to the power T. So this space increases double exponentially. So now for any dynamic decision problem, for any reasonable time horizon, all these problems are intractable. However, if there's more structure in the problem, so for example, Markovianity, then I can sequentially decompose this problem across time. Which means basically like a dynamic programming principle. And I can use that principle to solve such a problem. And it is known that for MDPs, Markov diffusion processes, the dynamic programming reduces the complexity of the problem from double exponential to linear in time. So there's a huge simplification that one can do if there's more structure. And if one can use this sequential decomposition idea, and that actually allows us to solve such problems practically. Now, the problem that I'm going to consider in this talk is as follows. So I have a follower and a leader, and I have a time horizon capital T. The follower observes a state xt, which evolves as a control Markov process. So probability of xt plus 1 given all x1 to t and a1 to t only depends on the past state xt and the past action at, where at are the actions of both the leader and the follower. And in this talk, I'm going to assume that both leader and the follower are taking actions simultaneously. However, I can generally in Stackelberg games, leader plays first and then the follower plays. But here I'm assuming both of them are simultaneously playing. But these are just minor tweaks. I can tweak from one to the other. It doesn't change the nature of the problem or the solution that I'm considering in this talk. So at any point of time, the follower observes the action history a1 to t minus 1 and its own state history x1 to t. Similarly, the leader observes the action history a1 to t minus 1, but it doesn't observe any state. So the action of the follower is a function of its information. Similarly, action of the leader is function of its own information, which is a1 to t minus 1. The follower gets an instantaneous reward RF, which is a function of the current state and current action. Similarly, leader is taking has a reward which is a function of xt and at. And I'm going to consider the notion of perfect Stackelberg equilibria, which is as follows. So perfect Stackelberg equilibria consists of two quantities, sigma tilde and mu. So sigma tilde is the strategy profile of the equilibrium strategy profile of the players, and mu is a belief profile. So mu as a function of any common history is an equilibrium belief on the follower's current state xt. So the perfect Stackelberg equilibrium is defined as follows. So given any strategy of the leader sigma L, the follower has a best response function BRF, which basically maximizes its reward to go for every time for every history for given that strategy sigma L. So it consists of all such strategies of the follower that belongs to this argmax. Similarly, for the leader maximizes its own reward to go for every time and for every history, uh, given that the follower's strategy belongs to the best response function of the sigma that it is optimizing over. So I'll just kind of repeat because it's a little complicated. So first I define a best response of the follower for every given strategy of the leader, and the leader maximizes its reward to go for every sigma L, where the follower then is playing the best response to sigma L. And then sigma tilde L and sigma tilde F is a perfect Stackelberg equilibrium of the game if sigma tilde F belongs to the best response of sigma tilde L and sigma tilde L satisfies equation number 4. All right. So before going further, I first want to talk a little bit about common agent approach. So in common agent approach, I have a belief pi t on xt, which is a probability on the state xt given the action history is a common belief on xt of the current state of the follower that only follower observes. And here I'm going to only consider Markovian equilibrium strategies, where the actions of the follower depends on the action history through pi t. Similarly, leaders action only depends on pi t. However, the equilibrium is defined in a space of general strategies. So the equilibrium itself is Markovian, but the deviations are in general space. Now, there's an equivalent way of defining strategies of the players using this formulation. So I can assume that the follower's action is taken through a function gamma tilde f that only depends on the state, where this gamma tilde f itself is a function of the state pi t. So basically, I can think of this strategy of the follower, which is a function of pi t and xt. I can first define it as a function of xt through gamma tilde f, and gamma tilde f itself is a function of pi t through theta ft. Similarly, I can define a strategy of the leader through gamma lt, where gamma lt is a function of pi t. Now it's easy to show that this pi t has a nice update structure. So pi t plus 1 is a function of pi t, gamma tf, and atf, and it's a base rule. Now I'm going to give you a simple algorithm to compute the equilibria. It consists of two parts, backward recursion and forward recursion. So in backward recursion, first I define the reward to go functions of the players at time capital T plus 1 is 0. And then I'm going to define these gamma tilde f, thus equilibrium gammas, as in a backward way as follows. So for each time t, first I'm going to define the best response of the follower for every gamma tl. So for every gamma tl, the followers has a best response function which is as follows. It maximizes the reward to go of the follower, where I'm maximizing over the follower's actions gamma tf. But one non-triviality here is that the solution of this gamma tilde f appears both here and in the update of pi t. So this is a fixed point equation for the follower. And fixing gamma tf, it solves as gamma tf for every gamma tl, for every gamma of the leader. So I solve this best response function of the follower for each time t. Then I say that gamma tilde L and gamma tilde F are solution of a fixed point equation if it exists, if the gamma tilde F is the best response of gamma tilde L, and the gamma tilde L maximizes the reward to go of the leader, where again the leader maximizes it over its actions gamma TL, and gamma TL, when I'm using gamma TL, the follower's action I'm using that is in the best response of gamma TL. So the leader maximizes its own reward to go, knowing that for every action it plays, the follower is going to play the best response of it. And if I have a pair such that gamma tilde F belongs to the best response of the gamma tilde L, and gamma tilde L solves this, then I have an equilibrium solution for that pi t. And then I plug it back in and find the reward to go in the same way I do it for the dynamic program. So in a backward recursive way, I can define this theta function. And then in a forward recursive way, I can define the equilibrium strategies and equilibrium beliefs as follows. So for initial, I have the equilibrium beliefs as the prior, and in a forward way, I will define the equilibrium strategies and the beliefs of the leader and the follower through these theta functions evaluated on the beliefs, and the beliefs are updated using the base rule. So if I do this, then I show that basically I have a perfect Stackelberg equilibrium of the game. I can also do it for the infinite horizon, but due to lack of time, I won't be able to talk about it. Finally, I want to take some example, show one example. So if I have the state X and L as binary, so it's a repeated game. And suppose this is my reward matrix for both the attacker and the defender. So attacker is basically the leader and defender is the follower. And these are the payoff matrices. Then using my algorithm, I can actually solve for the equilibrium strategies of the players. And it so happens that in this case, they are pure strategies as a function of the belief. This is when the state is low and the state is high. These are the strategies of the follower. These are the strategies of the leader and the utility function. Due to lack of time, I won't be able to go much into the detail, but like I'll just conclude by saying that in this case, we considered a game with one leader and one follower, where the follower has a private state that evolves as a control Markov process. We presented a novel dynamic programming-like methodology to sequentially decompose the problem of computing Markov perfect Stackelberg equilibrium of these games. We believe that this result can be extended to the case when the leader also has a private type, which we propose as future work. And in general, this algorithm can be used to increase the applicability of the Stackelberg security games in the dynamic security settings. And there are many applications of this, like information design, security, pricing, and more. And with this, I would like to conclude. Thank you.